All right, Zuhair. Okay, thank you for responding. Okay, so we have in this slide. Okay, this is basically what we have discussed last class related to EWMA. Okay, so exponentially weighted moving average. Okay, so why we need to use this EWMA? Okay, as we know that this EWMA is very powerful, especially for detecting of small shift. Okay, when we have small shift, when we say small shift, we are referring to shift of mean, which is 1.5 sigma or less. Okay, so that's small shift. So we also have discussed about Q-sum. Okay, so Q-sum also another alternative method of um, okay, monitoring small shift. Okay, however, this method also can be used. It can also be used if n is greater than one. Okay, greater than one. All right. What we do in this UMA control chart, okay, we need to plot the z value, which is given by lambda xi plus 1 minus lambda z minus 1. So the process target will be the mean. The mean is the process target, which is z node here, or the mean for the process. And lambda is normally taken as between 0 to 1. Okay, 0 to 1. So in terms of process variance, okay, we have sigma square is the variance, is the variance. So the variance is obtained by, as shown in this, okay, this is the variance, okay, the variance for the EUMA, which is the ZI. So it is given by, okay, this formula. So we have here lambda divided by 2 minus lambda and 1 minus 1 minus lambda and 2i. So as I mentioned earlier, last class, as the I get bigger, okay, this term can be dropped because it becomes 0 here as the I become bigger. So at the end, okay, we will have only um, okay for the control limits, upper control limit. Okay, initially we have all this term, which is 1 minus 1 lambda divided by 2 minus um, 2 minus lambda, 1 minus 1 minus lambda, and 2i. Okay, this is upper control limit, and this is lower control limit. The central line is the mean. So the format here is looks like Short control chart. Now you have the mean plus L. Okay, L is something that we need to decide. Okay, in design of UMA control chart. So L and lambda has to be decided. Okay, what sensitivity we like to have in this chart. So this is like having this okay the control limit. Okay, in Short control chart we have like 3 sigma, but in this case we have L sigma. Okay, and this is the term that influence the stability of the control chart. So when the number of sample increasing, okay, or rather subgroup is increasing, we have this I. Okay, this I become big, and then this term is not significant anymore. Okay, because 1 minus this becomes 0. Okay, 1 minus lambda. So just the this term lambda over 2 minus lambda will remain there. Okay. So what they call it at steady state. Okay, at steady state. Okay, so this value will become only this one. Okay, will become only this one. So this is what we have in the example here. Okay, so I think we have discussed this. Okay, just to revise again for you quickly to recall back what we have done. Okay, so this is UMA chart. Okay, the important is we have this, the mu here, upper control limit and lower control limit. If you see at the beginning of this, okay, it got like a step, okay, a step here until it gets stabilized. Okay, slowly gets stabilized. So when it's stabilized, okay, the control limit, initially the control limit is individual for each sample. Each sample. So as the observation number get bigger, it will become a steady state. Okay, at steady state, the formula for control limit is very simple. Just this one. Okay, the mean plus L sigma square root of lambda divided 2 minus lambda. Okay, for the upper control limit and lower control limit. So I hope you can try this. Okay, for your assignment, you can do it manually, but for sample of, just show sample of calculation. So you can also use Excel to do this calculation. But a few steps at the beginning, please show that to make sure that you understand the step of calculation of the control limits and also the UMA value, which is the Z value. The Z value is the UMA value. Okay. So this Z value, okay. So you keep calculating this Z for different sample. You can put in Excel if you like to have it, but I would like you to show a few sample sample of calculation to make sure that you understand what is showing in the calculation. So this example can be referred in solving that. Okay, so in this slide also we mentioned that some guideline in design of control chart. We design the control chart. Design control chart meaning that we are deciding what are the lambda to be used. Okay, because this will affect the control limits and also the L values. Okay, so these are example of okay, the range that is recommended between 0.05 until 0.25. Okay, but typical values that normally people use are these are the values commonly used. Okay, so who will decide this? Okay, it depends on the experience that you have in the process. You will decide the appropriate one. But the range is recommended between 0.00 to 0.02. Okay, in terms of L, okay, so the author of this book says that if L equal to 3, okay, which is usually referring to 3 sigma, can reasonably well in general application. Okay, so however, when lambda is small, okay, let's say 0.1, okay, so there is advantage in reducing the width of the limit, okay, by using a value of L which is 2.6 and 2.8. Since the lambda is small, okay, it's recommended that we can reduce, okay, instead of using L equal to 3, we can use L equal to 2.6 and 2.8 or 2.8, meaning less than 3. So, okay, so this is some, based on previous user by others. Okay, this is what they recommend. Okay, so we can expect the choice of parameter to result ARL for control process, which is 500. Okay, you see here, EWMA is quite powerful. If we compare with Shewhart, if Shewhart, we see that 370. Okay, Shewhart control chart, X bar chart, ARL for stable process is 370. But in this UMA, ARL can go to 500. Okay, about 500. So this is considered as a good control charting procedures because it get less false alarm. It get less false alarm. So it says here that one standard deviation in the mean of ARL for unstable is 10.3. So if we compare to QSUM, okay, remember that we also have QSUM. This is equivalent to QSUM having the design parameter of H equal to 5 and K equal to 1/2. Okay, there are also some disadvantage of using this, especially what we call it the initial effect, which reduce the effectiveness of UMA, okay, in shift detection. Okay, signal resistant, okay, because at the beginning, this might have some disadvantage of using UMA because there is initial effect. So another disadvantage is UMA okay, may not be able to detect big shift. Okay, it's very sensitive for small shift, but big shift is not so sensitive. Okay, so as we can see from here, UMA perform well against small shift, but does not react to large shift as quick as SURE. Okay, so it's good in small shift, but when we use in big shift, okay, it's not as good as SURE control chart. SURE control chart referring to X bar chart. So what we do is we can combine, we can use both SURE and UMA control chart jointly together. Okay, so if you want to get benefit of both, sensitive for large shift and also sensitive for small shift, we can combine SURE and UMA control chart used together jointly, so that we can detect small shift and also large shift, okay, concurrently. So it's very important for us to understand what type of shift that you are having in your process. Okay, another advantage of UMA, okay, we see that in SURE control chart, okay, we always make assumption that the data is independent and identically normally distributed, okay, identical and independently distributed. But this is not always true, especially when we are taking a single data, individual data. Okay, so we may have non-normality, okay, non-normality, where the process data is not following normal distribution. Okay, however, this UMA is not sensitive to normality. Okay, so it can be, remember that before this I discussed about a method how we can eliminate or can reduce the effect of non-normality. Okay, do you still remember what is the method of control charting that we try to minimize the effect of non-normality? Anyone? Please respond. Can you put in chat box? Also, you can voice, turn on your mic to answer this. Okay, what is the techniques to eliminate the effect of non-normality? We have learned about one techniques before. Nobody want to respond? Okay, I call a name here, right? Okay, who is E Kong Chun? E Kong Chun? Yes. Okay. What is the method? Okay, what is the method to reduce or to eliminate the effect of non-normality? The charting techniques that we have discussed previously. Okay, please respond. So everybody is quiet. So this is not interesting. So I have 38 online. Okay. Okay, non-parametric test. Okay, what is the charting techniques? What is the charting technique? Yes, it is non-parametrics. Okay, because there is not following the any distribution. Not as test. Okay, not as test. The RL no. What is the control chart? I did mention about transformation. Okay, what is the transformation that we use? Okay, the transformation. What transformation we can use to minimize non-normal data? Not Six Sigma. Okay, what is the method? Yes, this is using log. So siapa yang jawab ni? Okay, use log. Okay, Faiz. Okay, Faiz, you got it correct. Okay, we use log transformation and natural logs. Okay, so at least adalah orang ingat. The others, if you may forget, okay, so you have to review balik. Okay, we use log transformation of the data before we plot. Okay. Log transformation. Okay, log transformation. Okay, so in the case of using UMA, okay, UMA, the advantage is it's not so sensitive to the non-normal. So meaning that it can be used. Okay, it can be used for non-normality. Okay, let me go back to the slide. Okay, why my screen is not showing? Okay, I got it here. Okay, you can see the slide, right? Okay. Okay, so as I just mentioned just now that this UMA can be used in the case of non-normality. It's quite robust. Okay, it's quite robust. So okay, as mentioned here, ARL performance of Short individual chart and EW control chart for the case of non-normal distribution. Okay. Okay, this author, okay, this author they make comparison. Okay, they make comparison. So they use a gamma distribution to represent the skew distribution and so on. Okay. Okay, how come my slide that's not moving? Okay, so it's recommended. Okay, we would recommend that. Okay, this author recommended that. Okay, the design of UMA as a control chart for individual measurement in a wide range of application, particularly phase 2 process monitoring. It means that after we do the revision, we have eliminated assignable costs. Here we have the revised control chart. So it's recommended that we use UMA, okay, for individual measurement, for individual process monitoring, okay, because it is robust, it's not so sensitive for non-normality, okay, and also it can detect, okay, effectively for single data, for individual data. All right, I think that's all for this, what we have discussed last time. Okay, let me share with you the new slide for today. Will be on the other chart, the type of charts. Okay, before that, maybe I show this again to you. Okay, for those who have forgotten about this, the individual, yes, it's the one. Okay, do you see my slide now? This is related to the individual, with the individual measurement. Okay, that was the lecture before we discussed about UMA and also QSAM. Okay, this is individual measurement. Okay, for the individual values. So, okay, please respond. I want to know whether you see the slide as shown. Okay, yes, you can see it, correct. Okay, so the individual measurement. So we have discussed this. Okay, there are methods for individual measurement for moving, what we call it, moving range. Okay, the moving range, MR, okay, the moving range, where we have the individual control chart. So like what I discussed just now, the UMA is effective for individual values. Okay, we also previously we also have this control chart for individual unit based on SURE, but of course it's not so as good as UMA individual. But anyway, that is a method that people have used before they are able to use the individual UMA. They try to use this. So where we have this moving range and X values are plotted. Okay, this is our individual, not the mean value, the individual values. Okay, so and they found out that these individual values are sensitive and not so good when there is non-normality. Okay, then there is non-normality. So that's why after that we discuss about this new charting, okay, where we transfer the data using natural log, okay, the natural logs. So what was plotted was natural log. Okay, this is the natural log data rather than the raw data. Okay, so in this chart we have the natural log of X, the observed value, and the moving range. Okay, the moving range rather than the raw data X value and the moving range. But now we try to eliminate the effect of non-normality by transferring it to natural log. Okay, please read these notes. So we have mentioned it here, that transformation, transformation. Okay, especially mentioned the normality assumption. Important to check the normality assumption when using control chart for individual, especially when you are using SURE-based chart. Okay, need to check normality. So the way that we check is through normal probability plots. Okay, if all the points are close to this line, shows that it's a good normal distribution. But in this case, there are some points which is deviate from that line. Okay, so in order to solve this, Okay, so we take this natural log. Okay, natural log. Okay, for this data, we have 25 data. Okay, for all 25 data, so we take the natural logs. Okay, natural log. So when it is plot, first we check this comparison between the normal data, okay, for the raw data before transformation, and this is the data after we transform into natural log. So we see here the data is closer to the line, okay, compared to this. Some data is deviate from the line there. So these are the plots. Okay. So that is related to okay. Okay, now let me share the new one. Okay, what I want to show now is okay, other control charts. Here are the control charts. Here are the control chart. Okay, this is here. Okay, in your ebooks is chapter 10 of your ebooks. Okay, let me, where is the, okay, here, sharing. Okay, I hope you are able to see this. Okay, do you see this? Please respond to chat box. Do you see this or not? Chapter 10, yes, okay, good. Okay, chapter 10 of your ebooks is talking about univariate, still univariate. We are discussing now univariate because in control chart there are univariate, there are bivariates, and bivariate mean that two variables. So far we are just monitoring one variables. There are cases where we are monitoring two variables concurrently. So far the control chart that we have discussed is only for univariate. Okay, univariate means you are only monitor one parameter. It could be thickness, it could be surface roughness, it could be resistance, or it could be current fluctuation, any parameters. Okay, only one parameter. But there are cases that we need to monitor more than one concurrently. For example, diameter, internal diameter and external diameter need to be concurrently monitored. Those are, we call it bivariate. Okay, we will discuss that later, how to monitor two parameters concurrently. Sometimes monitoring one parameter alone is not enough, okay, for the purpose of quality monitoring. For example, you have a bearing. Okay, bearing, you have internal diameter and external diameter. Both are important because it creates the thickness. Okay, maybe I sketch here. Okay, you have a bearing that, okay, you have this diameter and this diameter. Okay, both are important. How could we monitor this on control chart? Using the chart that you have learned so far, it cannot. It is not giving you accurate results, because if you monitor one chart is monitoring, let's say this is D1, this is D2, meaning that you have a control chart, let's say you either using UMA or you are using Shewhart. Okay, you are monitoring only D1 control chart here, and you need another chart for monitoring D2, meaning like two charts. Okay, so this can be misleading. Can be misleading. So we need another chart special for bivariate, where we can concurrently only on one chart, we monitor both D1 and D2. This is, we call it bivariate. okay, bivariate control charts. Okay, hopefully by next week I can explain a little bit on this bivariate. So what we do so far is univariate. Okay, univariate. So univariate meaning that you only monitor only one parameter. Okay, only one chart decide the quality of a product. As we know that in a product, you have many parameters, which is critical to quality. It could be holes, it could be thickness, it could be position between two holes, and so on. So if we are using univariate, okay, especially when the features on the products are related. Okay, let's say you have two holes. You have a piece of component, two holes. One hole is here, another one is here. Okay, so the important is the distance between these two. Okay, so the distance between these two is important. So you need to concurrently monitor this the diameter of this hole so that you can get good fitting. So if we monitor this hole individually, so it's not going to be a good quality monitoring there. Okay, so the method that we have learned so far is not able to monitor this bivariate. Okay, because what we do is only univariate. Okay, univariate. So before we can understand the bivariate, we also need to understand. We must understand first the univariate. Of course, this bivariate is more complex in terms of statistics. Okay, so in the univariate case, it's also similar to bivariate and so on. That will require advanced level. But I would like to highlight here, there are cases where we have what we call it short run production. If short run production. Most of the control chart, traditionally, it was invented for the purpose of long run production. Okay, long run meaning that the production is running for long period of time. But because of the short product life cycle nowadays, so some product is only produced for a short period of time and then changed to another model, another design. Okay, if you see now many products, the life cycle is very short. Okay, you can get a new model every 6 months, for example. So the production is not as long as in the past. So this is the challenge that we face in control charting, where the production is so limited. How can we monitor the quality? So this is the issue of what we call it short run production. Okay, so another issue that we are facing is many process now, they go multi-stream. Okay, multi-stream. So not only one unit is out from the process, but multiple product is out. For example, in injection molding, you may have the head of this molding, for example. Okay, let's say I have 3 head. Every time you press, okay, you press this head, okay, you may have 3 item out. Okay, 3 item out. So how can we monitor this? These are the challenge. So because of the traditional control chart, it's assuming that it is coming out only from one head. Okay, press here, only one head is out. Okay, so we are very sure that this head is causing the problem. But now you have head number 1, head number 2, head number 3. Can we combine this together in a control chart? Okay, we have to be careful, okay, when we want to combine. This is the issue of what we call it multi-stream process. Okay, so the traditional method of simple control chart will not be suitable in that case of multi-stream. Okay, so we have short run is the challenge now. Okay, multi-stream is a new challenge. Okay, in the past I mentioned about the single because due to automation, the production now are able to be measured individually. So the traditional X-bar chart is being challenged with a new process situation. Here we also have another challenge, what we call this autocorrelated. So this is another challenge. Okay, autocorrelated process. Okay, this autocorrelated process is happening in chemical industries, and also it happen in automation. Okay, in automation, autocorrelation is the issue, because in typical control chart, we are assuming our assumption is independent and identically distributed. The data that we have is IID. This is our assumption. But we found out that when it is running automation, this IID is not fully satisfied. Okay. So, okay, the other one I think I will not cover, but I will touch on these three issues, which is short run, and we have multiple stream and autocorrelated. Okay, let's see the first one. Okay, when we have short run production, okay. So as mentioned here, okay, we see that statistical process control be found wide application in almost every type of businesses. Okay, control chart is not only in manufacturing, so even people in banking, okay, they use control chart for monitoring the processes, for example, check clearance, the processes of loan application. Okay, we have like attribute control chart that we have not discussed yet. So even in hospital, they are using control chart to monitor activities. As long as there is a process, you can use control charts. They can use control, not only for monitoring processes in manufacturing. Okay, so okay, job shop. Okay, what it says here is job shop manufacturing. Job shop manufacturing. When we say job shop, okay, job shop is normally short run production. Job shop. When you have job shop, you will have the characteristic of job shop. It is low volume, high variety. Okay, low volume meaning that one model you don't produce too much. Okay, the quantity is low, but the variety is high. Meaning that you have many models. This is job shop. Job shop style of production. But the typical control chart has been invented for the purpose of mass production. Okay, in the mass production, where you have similar model, okay, you produce it in high quantity, meaning that similar model, okay, high volume, okay, high volume production. So this is typically the control chart. Traditionally, it was used for mass production, but due to the demand from customer need a variety of model. They do not want to have similar product with other customer. So there will be many variety, many models. And this every time they produce a model is low volume. So how can we address the variability in the process using control chart? So this is what we call it short run production. Okay? Short run production issues, or short production runs. So what we do here is we use what we call it control chart based on deviation from nominal. Okay, we use D chart, okay, deviation, rather than using the raw measurement data. We plot the deviation. Okay, remember this deviation. Okay, deviation chart. Okay, what is deviation chart? Okay, let me show it here. Okay, we still can use X bar and R chart. Okay, but the control chart will need to be modified. Okay, need to be modified. Okay, which is we call it deviation from normal, which is denorm control chart. Okay, so what we're using is denorm, deviation from normal. Okay, denorm control chart. So what we do in this denorm, okay, let's say the data is given in table 10.1. Okay, let me show this table. Oops. Okay, this table 10.1. You have three different parts. Oh, sorry, you have here two parts. Huh? Only two parts. It's showing that only two parts. Okay, part A. Okay, and then you move to part B. So meaning that you already switch your production to a different part. So we cannot produce control chart only four. Okay, not enough. Okay, it's not enough. Okay, and then after that we stop and produce another part. This is part B. So now, how could we prepare the control chart? So what we do is, let's say here, okay, you have three parts, three unit, M1, M2, M3. These are the measured value. Okay, the measured value. You see the measured value here? Okay, let me put example here. Let's say A is just produce a pin of this size. Okay, you monitor the diameter of the pin. Okay, B is also the pin but smaller size. Or smaller size. A pin of a smaller size. So how can we use similar chart? Okay, cannot unless we modify this. Okay, you see here the B, the dimension is between 24, 25, 27, but here is 50, 51, 52. So typical control chart cannot be used. What we use is we look at deviation. Okay, deviation from nominal. Okay, so instead of plotting 50, 51, 52, we plot the deviation. Okay, so before we plot deviation, we have to see what is the nominal. Okay, in this case, the nominal is 50. Okay, 50. So what we do is 50 minus 50, you get 0. Okay, and then you have 51 minus 50, you got 1. 52 minus 50, you got 2. Okay, and then you get the average of here, okay, 1, and the range is 2 minus 0 is 2. Okay, still have X bar chart and R chart. Okay, continue with the second data. 49 minus 50 got minus 1. 50 minus 50 got 0. 51 minus 50 got 1. Okay, take the average of this. Okay, you got 0 divided by 3, so it's 0. The R is okay, between minus 1 and 1, so it's 2. Continue until you finish here. Okay, now you have the component B. B, the measurement is starting at 24, 27, 26, not 50s, because it's smaller size. So what you do here, so we have to take what is the nominal here. The nominal here is 25. Okay, the nominal value for this is 25. Okay, so 24 minus 25, you got minus 1. 27 minus 25 is 2. 26 minus 25 is 1. 25 minus 25 is 0, and carry on, so on. So at the end, you still got X bar, X double bar, and R bar. Okay, so we still have this value, but the way that we make the calculation is, okay, we have to take the deviation. Okay, remember, it's deviation, not the raw data. We plot the deviation. I hope everyone follow this. Okay, so if we go back to this is based on what I've just mentioned just now. For the part A, say part A, okay? So the part A nominal parameter is 50, okay? So the M represent the actual sample of measurement, this actual measurement, okay? This is the nominal. So we got the XI, okay? So the deviation, okay, it shows that now consider as I discussed just now, that's how we collect the deviation. So this value is the deviation, okay, what we call it denorm, deviation from nominal value. Okay, deviation from nominal value. Okay, why it's not moving? Okay. Okay. So for the second product just now, the B product, okay, the nominal was 25. Okay, so we also get the deviation from nominal. Okay, after that we have the control chart X and R using the deviation from nominal as shown in the table. Okay, so in practice we recommend until you have 20 sample, okay, before calculation of control limits. Okay, so but in this example just use 10 sample for the purpose of example only, but for practice, okay, we cannot have a control chart which is less than 20. Normally minimum 20, and I say earlier 20 to 30, but good practice can be 25, okay, but not less than 20. Okay, so three important points that we need to highlight here related to denorm, okay, deviation from nominal control chart. Assumption that the process standard deviation is approximately the same. Okay, we assume that standard deviation are the same for different component just now. Okay, for all the parts. Okay, if the assumption is not valid, we need to use standardized X bar and R chart. Okay, so this procedure works best when sample size is constant for all the parts. The sample size that we see just now, it was n equal to 3. Okay, all parts we are getting 3. So if the sample size is varies, still can be used, but it's not going to be the best lah. Okay, it's going to be to create maybe some factor contributing to variability there. Deviation nominal, deviation for nominal chart have intuitive appeal when nominal specification is the desired target value. Okay, so if the nominal is the nominal is the target value, okay, so this method will work effectively. Okay, so let's see how we can plot this chart. How can we plot this chart? Okay. All right. So this is the plot of the chart. So we have A in this part, okay, A on the left, B on the right. Okay, we are plotting deviation. Okay, we are plotting deviation here, and we are plotting sample range. Okay, still can have control chart here, but this is denorm control chart. We can also use the standardized X bar and R chart in the case of the assumption of standard deviation are not same for different products. We need to use standardized X bar and R. Okay. So I think the time is up now, but please go through your ebooks on the topics of multiple stream, okay, and autocorrelated. This is what I will discuss next class. At the same time, please do your assignment for you to get a better understanding about the control charting. Any question before I finish? Hello, any question?
No, sir.
If no question, that's all for today. Thank you very much. Okay, I see you next week. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr.